So last time we did section 2. Well, we did 1.4, and then we did part of 2.1. And I actually got almost all the way through 2.1 as I got to looking at what I had done. Today I will finish 2.1, and I've already planned in advance in the syllabus to only get halfway through 2.2. And in fact, the authors of the textbook figure that's going to happen too, because they broke the homework lesson into two parts. So there's 2.2a and 2.2b, and I have different due dates on those. Okay, so it seems like every time after class I have to go in and adjust the due date, but I don't remember to do it until somebody reminds me. And then, so if you go in there and go, oh my God, that's due. I don't know how to do these problems yet. Just email me and say, hey, is this really due coming up? It'll remind me to change that due date. Okay? So what I want to do today is partially out of the book, but a lot of looking at the data that you guys sent in. I now have that processed, at least part way. And so a lot of the graphs that they talk about in section 2.2, we'll use your data and show those same graphs. I will say right up front that there's about 6 or 8 different types of graphs that they talk about, and I don't do all of those in class, so just read them. They're pretty easy. The one that I personally hate is a pie chart. You ever see pie charts? All the time. They're worthless. I don't like pie charts, so I'll show you what one is, tell you how to read it, but I'm not going to teach you how to make one, and I went into the homework and I deleted out the ones that have you figure out the central angle and all that. So all you're going to have to do from a pie chart is look at it and it'll ask questions like, what % of the sample was in this wedge or whatever? Okay? But then other than that, I want to start with something that's not really in the book, but looking at your data. Do you remember what I said is the first step always when you get real data? After you've collected the data, what do you suppose the first thing you have to do is? What if I handed you this data and I said, hey, do a histogram of pulse? Okay, analyze it, but before you can even analyze it. Well, I'll tell you what. Let me scroll down through this. And unfortunately for the recording, they won't be able to see the screen while I'm doing this. But you need to clean the data. What does that mean, clean the data?
Get rid of the ones that would throw off
Get rid of problems. Remember the processing errors that we talked about last time? Well, that's the first thing we're going to do is look for processing errors. So I'm going to scroll down through here, and you tell me if you see anything that looks odd. And this is actually the first step I do when I get a data set, is I visually look at it. Because a lot of times things that are odd will just pop right out and you go, ooh, that looks weird. And you'll catch them before you have to even load it into the computer, other than it being in a spreadsheet or something. But I can't remember how far I have to go down before things start looking weird, but there are some weirdnesses. Okay, do you see that? What happened here? I don't know. Yeah, it's out of whack. Well, that's a clue that something's different. So what it turned out to be, when I went ahead and read this data in to the software that I use, and oh, this is what I want. And as the first step, looking for process errors, I went and I saw those problems, but I thought, I wonder what this looks like when I go into the software and tell it to do some frequency tables. So I ran some frequency tables just looking for things that look odd. So this is part of the data cleaning process. So the first thing I did was I ran by section and initials. So section C, that's you guys, right? This person, BDT, is that person here? Who's BDT? Oh, you don't want to admit it, huh? Whose last name begins with a T? It might be, okay. BDT, there's only 3 observations. How come you only turned in 3 observations? Exactly. She turned in all 6, or all 5. But if you go back to the spreadsheet, that's you, BDT, right? What happened is you put a carriage return right there, which in Excel, when you do a carriage return, it just jumps to the next cell down. Perfectly fine. But in the Google Doc, apparently, a carriage return is different than tabbing down or whatever. And this happened quite a few times in here, not just you, right? And it happens sometimes on things over here. But when I ran it in SAS, is the name of the software that I use, it not only told me that you only had 3 and other people had less than 5, but it also told me I had more than one section C. They looked the same, but one of them was C with a carriage return and one was C. So the computer thinks those things are different. Okay, so that's one issue that I found. This one caught my eye, but it turns out there's nothing wrong with it. It's just for some reason, whoever that person is justified the D instead of centering it. So that's no big deal. But then here's another C, H, N, M. Who's that? So you had the same thing, carriage return. And you had one under an N here. Same thing. You know, and like I say, in Excel, that's perfectly fine. But for some reason, the Google Doc treats it different. So those are processing errors, but not really data entry errors. Here's one from my online class. DED put a carriage return under each of their set of initials. So it got weird. And then, let's see, I'm starting to get close to the bottom. There's another C with a carriage return. And there's the bottom. See anything? What do you see? No's and yeses. Right? And someone else in the online class had the inches after there. Right? Well, what my software did when it read those in, it said, hey, this is a numeric variable. You're trying to enter character strings, so it just set it to missing. So when I ran the frequency tables, I thought, well, how come I have 5 missing values for height? So then I went back in and found, oh, there's one where they put inches. Right? And then this person in the next section, so I get to wait an hour before I make fun of them. But it's funny because they entered it into the Google Doc. They were the very last person and didn't quite make the deadline, but the very last person didn't bother to look up here and see, oh, that's not matching everybody else, and just hurried it in there. But so first thing I got to do before I process the data is clean all this stuff up. Then read it in. Otherwise, it can kind of, you're throwing away data if you don't take care of it. So this is what it looked like when I ran a frequency table on the exercise variable. It thought there were 4 levels or 4 categories for exercise. N's, no's, y's, and yeses. Right? And here's those 5 observations. Everybody else did good. Okay, so just a little bit of a discussion about in real life, when you deal with real data, there's going to be problems. Just know that going into it. And you have to set a time aside to get the data clean before you can analyze it. It sometimes takes longer to clean the data than it does to analyze it. Okay, so now, after the data is cleaned, I've run the frequency tables. I showed you these last time, so I'm not going to dwell on these and talk about how they're done. We did that last time. But last time was old data. This is your data. Right? So we had a total of 365 observations this semester. And remember last time I said usually it's 50-50? but last semester it was 60-40 males, females. Same thing. So guys, take heart. The gender makeup at the university is swinging in your favor. I know, that was bad. All right, so exercise. We have about 60-40. You remember what it was last in the old data I showed you last time? It was more like 70-30. It was way out of whack. This is still way different than the general population. Right? 60% of the general adult population don't exercise. Smoking, pretty close to what it was before. I think it was 88 and 12, and now it's 89 and 11% smoking. So that's a good thing. Health rating. These numbers are so close to what they were last semester when I showed. I thought, did I not get that updated? But I did. I verified. There was one person who rated their health as poor, just like there was before. And last time, and this was a 33, this semester it's a 32. So the numbers are very close. So typical, when you get to 5, only 10% of people say they're in excellent health, but most people fall either into a 3 or a 4. Okay? So now, the first kind of graph that goes along with a categorical variable. It's called a bar chart. It's really the same thing as what we'll show in a minute called a histogram, only they switch names when you go from a categorical variable to a quantitative variable, a numeric variable. So when we go to height and pulse and those things, we'll call them histograms, but it's really the same thing. So how do we read one of these? Well, over here, this particular one is called a percent bar graph. You can also have a frequency bar graph. So over here I have percent. These numbers are small, so they're probably hard to read, but 0, 2, 4, and so on. So the height of the bar represents, this one looks like it's at 9%. What does that represent? 9% rated their health as fair. Good. I'll scroll back up to the table. 8.77%, about 9%. Right? So you're just taking these numbers, the percents, and drawing a bar that has a y-axis labeled as percents, and you're just drawing a horizontal over, and that's how tall you draw the bar. Right? It's useful. I didn't do it, but sometimes it's useful. You can tell the software to actually print the number above the bar. So you don't have to come over and figure out, it looks like it's about 9. It's just written right there, 9%. Right? So this shows just barely a sliver over here at 1. Then the 2s and the 5s are pretty even, and the 3s and the 4s are fairly even. Right? With the vast majority of people saying either a 3 or a 4. People want to be good, but not too good. Now this is known as a side-by-side bar chart. And these can be done in different ways. This was the default way that my software does it. It's actually not my favorite, but I ran out of time to figure out how to do it the other way. But it will do it the other way. But the other way is to use different colors, but set the ones next to each other. So you have a 1, 2, 3, 4, and 5. And then you have, let's see, 0, and then there's a 1. And then when we go to the 2s, it looks like, I'll make it up. Looks like out there, and then about there. And use a different color or symbol. So the 3, so this is going to be smokers, non-smokers, smokers, non-smokers. So you draw the bars side by side, and they're intermingled into one graph. See what I'm doing? Either way, what's the purpose of doing something like this? So notice that I used as my classification variable the smoke variable. It's probably too small to read, but that says smoke, and this is a Y, and this is an N. So these are my smokers. These are my non-smokers. Exactly. So you can see the relationship between how people rate their health and whether or not they smoke. Right? You'd see the same thing here. The way it works is actually those I think are fairly even at the 3, and then at the 4 and the 5 it looks kind of like that, where the smoker bar is taller in the early lower ratings, and then it flips, right? So what do you see here? The ones, there's not enough to really compare, but at a health rating of fair, you don't have near as many non-smokers as you do smokers that say they're only in fair health. And then these are fairly even. Smokers a little bit higher. And then what happens when you get to 4? It flips, right? The smokers are lower. There's not as many smokers say they're a 4 or a 5 as there are non-smokers. Right? That's what we will learn is called association or relationship. There is an association between whether or not people smoke and how they rate their health. Smokers tend to think of themselves, remember this is self-reported health rating, but smokers tend to think of themselves as less healthy than non-smokers. Kind of interesting. Okay, when we go to a continuous variable like pulse, quantitative variable, you can do a frequency table just like we did with categorical variables, but you divide into classes. Right? So let's spend a little bit of time and talk about where do you get these classes, because you got homework problems that are going to make you do this. So, and then we'll talk about what it looks like after we do that. So in our data, I ran the analyses and I said, okay, what's the minimum heart rate that somebody turned in and what's the maximum heart rate turned in? You'll need those two numbers to decide your classes. Okay? So the let's let K equal the number of classes that you want. Now remember last time I talked a little bit about deciding what K is. Right? The more data you have, the more classes you can use, because you won't have a lot of empty ones. The book talks about it in just about that much detail and says, well, for this class, we'll just tell you what K is. We'll say, make a histogram using 7 classes, or 5 classes, or 27, or whatever. So, if K is the number of classes, then the next thing is to determine the class width. So, to get the class width, you need to know what the maximum value is in the data set and the minimum value in the data set. So you span that range. And then each class what would you do with this difference? Divided by K. Very good. All right? So in our data, that turned out to be 126. That was the maximum heart rate turned in. Yeah, that's big, isn't it? We'll come back to discussions of the data in a second. The minimum value was a 40. So we had 126 minus 40 over, let's use 10 for number of classes to start with. Right? So when you do that, if you do that on your calculator, you get 8.6, which is fine, but use a little common sense and think, well, okay, 8.6. That's an odd number to be dealing with. That's about 10. Let's call it 10. And in fact, what I did is said, well, 126, that's about 130. It's a nice round to the nearest 10. And minus 40. And I thought, well, if I go down to 30, then I get a distance of 100 divided by 10, and I get 10. A nice bar width, right? So it's perfectly fine to adjust that bar width to make it reasonable. Make it easy to work with. It isn't going to make a whole lot of difference in the way it looks. And I'll show you several different class widths when we go to pulse, and you'll see how it changes. This amount of difference wouldn't change very much. Okay? So that's how you get the class width. So then the next thing you do is you start at your lowest value, 40, and figure, okay, what's a reasonable place to start that includes that minimum value, right? So what did I say our minimum was? 40. So if I use class as a width 10, where's a good place to start? 40. Yeah, good. So what they call the lower class limit is reasonable choice at or below minimum value. In this case, that'll be a 40. But what if my minimum had been 42? I'd still start at 40. There's nothing wrong with starting at 42 and going 42 to 52, 52 to 62. But that's just not as easy. It's easier to use nice multiples of 10 and go 40 to 50, 50 to 60. So I'd probably start at 40 even if my minimum was 42. Right? Okay, then the upper class limit. Same kind of idea, reasonable choice at or above the max value. So I'll just abbreviate all that. At or above max. So where am I going to stop? 130. My max value is 126, so I'm going to go to 130. All right? So I'll make classes. So then the next step is to make your frequency table and start, well, I started at 40, and I need to go up to what? 49. Very good. I didn't expect to get the correct answer the first attempt. And then the next class is 50 to 59, and so on. Now, why did you stop at 49? Well, in the data, nobody turned in any decimals. Everything was a whole number, right? So I can stop at 49 and I get everybody that's less than 50. Right? The next class, so the starting point for the classes includes that value. Right? And they're going to be 10 units apart because that's my class width. So you start at the beginning, you just add 10, and you say, okay, where do I stop this one? Stop it at the next number below the start of the next class. If they're all integers, you can stop at 49. What if I had 2 decimal places? Then I would go 40 to 49.99. 50 to 59.99. Just so the number of decimal places you have in your data dictates how close you get. Some software will write it this way. 40 to less than 50. And that covers you even if you have an infinite number of decimal places. Almost. Okay? Now there's one more definition that they give in the book. Yeah, question?
Okay. So for the lower class limit, you said that the minimum value is 40. But for the upper class limit, you said the maximum value is 130.
Yes. So at or above the what?
Why would that be 126?
Well, I'm going to start at a nice multiple of 10, right? So I've decided to start at 40, and I have class widths of 10, so each limit has to be a multiple of 10. So I need the next multiple of 10 that covers my max. So at or above the max. Right? That's a good question I forgot to say, but you're going to start at the bottom and go up according to your class width. Right? Okay? Now, they talk about class boundaries, and I don't find this to be all that important, but I'm going to go ahead and talk about it. But class boundaries are halfway between these two numbers. Right? So it's a number that your data can't be, so it's going to break right at that value. So anything above 49.5 goes into the next class above. Anything less than 49.5 goes into this class. So it's just halfway between the upper limit of one class and the lower limit of the next class after that. Class boundary. Then they talk about class midpoints. And I'll give you the way they do it in the book, but I would do it slightly different just because it doesn't really make any difference and it seems more reasonable. Class midpoint is lower limit plus upper limit divided by 2. In other words, the average of the lower and the upper limit. So what's my midpoint of this first class? It's not a trick question. 44.5. 40 plus 49 is 89. Divide by 2, you get 44.5. So 44.5. Now, to me, it works just as well to go lower plus next lower and divide by 2. And then what would I get? 40 plus 50 divided by 2 is 45. Doesn't that seem more reasonable that, well, 45 is the midpoint of this one, 55, 65, and so on. But again, it really doesn't make a whole lot of difference, but technically this is the way the book defines it. So when you do it on the homework, you're going to need to use that method. Okay, so let's go back into the data. So here is my frequency table. I had 30 to 39, but there weren't any subjects in that class. So then you would just delete that class back out if you didn't end up needing it, right? In 40 to 49, there are actually 5 subjects. That's 1.37%. And as we go down, you can see that these two, 60 to 69 and 70 to 79, tied. Just coincidence, but they tied. And cumulative frequency and percentages as we go down. This is where it becomes useful. Those cumulative frequencies become useful. This is not going to be defined yet for a few sections down the road, but you know what a percentile is? What's it mean if you were at the 80th percentile? Okay, that's right. So the 80th percentile means that 80% of the population or the data falls below that value. Well, cumulative frequencies or cumulative percents let you see those, only not to nice round number, but 93.15% were at 89 or below. Right? So the 93rd percentile is 89. So you can use your cumulative frequencies and cumulative percents to look at it that way. There'll be a graph that I'm not going to show you, but it's in the book, that is a bar graph of cumulative frequencies. It's called an ogive. That's a funny word. I've never remembered to go look up where that word came from. It just doesn't seem like a word I've ever encountered before. So here is a bar graph for that frequency table we just showed. So, oh, and I forgot to say, how do you form that frequency table? Once you have it all laid out, 40 to 49, 50 to 59, all the way down to 120 to 129. Now, how do you figure out what the frequencies are?
Many people are listed in that.
Okay. And how would you physically do that?
Look at the values.
Okay, exactly. Look at the values. Well, let's look at the values. I got to go into this spreadsheet, and this is my pulse here, and oh, there's a 65. Count how many fall in the 60 to 69 category. You got to go through 365 observations and put tally marks, right? So you're in your 40 to 49 group, and you go down, every time you hit one that's between 40 and 49, you put a tally in there. Does that seem like that might be a little bit tedious? Yeah.
Did you just organize it and have it counted for you?
Yes, the software can do this for you, right? Excel, Microsoft Excel can do histograms and frequency tables, that kind of thing. It's not, I don't have time in a class like this to teach you to use the software other than your calculator. Your calculator can actually do histograms and frequency tables too, and that is posted in the Chapter 2 technology thing that I'll give you, but it's also in your book. They show you how to do it in your book. But you could also, if worse came to worse, you would sort the data. You just click in a column, tell Excel to sort it, and then at least you can say, okay, here's my 40, 40, 40. You can go down this many, we're in that group, and then you count to the next group and so on. At least they're in order for you. It's still fairly tedious. Okay, so that's what it looks like. How would you describe this distribution? It's the shape of the distribution that we're going to become, will become important to us. How would you describe the shape of this distribution? What'd you say? An H? Well, she said normal curve. You've heard of some of this before, right? Yeah.
Is it your bell-shaped curve where the majority of the
Yeah, which is a normal curve, right? And it looks pretty bell-shaped, right? But you've got some outliers up here, right? There's actually two observations in this cell, right? There's a 124 in the data and a 126. They did not come from the same person. By the way, as we talk about outliers, one of the things when you're cleaning data, when you identify outliers, is you see, are they real? Or was it a typo? Can I fix it? So I emailed the person that had sent in the 126. And I got a response back from her and said, well, I actually wondered about that one myself and thought she may not have taken it correctly. So she was letting the person take it. But I said, if you can, retake it. And let's see what it is. But I haven't heard back. Right? But she said that person is overweight, is a smoker, and does not exercise at all. So it may very well be a real value. Right? The 126 is still really high for that. I had a number that was up in the upper 120s one semester. And it happened to come from somebody who was in one of my day classes. This one I'm talking about today came from the online class. But anyway, she was sitting in the class. And he goes, oh, that one is mine. And I said, what do you know about that person? She goes, I work down here at the drug rehabilitation center. Right? She's a counselor there. And so I interviewed my patients. And that guy was high on meth that day. It's like, oh, well, that explains it. Right? So, outliers. See if they're real. If not real, can you fix them? If they are real, now what do you do? Well, you have to make a decision. And the decision depends on, well, what am I trying to do with this data? If I'm trying to say, what's the typical person, heart rate-wise, then I wouldn't want the meth guy in there. That's not typical, right? But otherwise, maybe you keep it. If it's a real value and you throw away the ones that just look weird to you, you're biasing the data. So. Okay, so here are some basic summary statistics from the pulse data. So you see that the mean pulse was about 72.4. So average pulse is about 72 beats a minute. Right? Standard deviation is a measure of variability. We'll talk about that very soon, but about around 12. Every single semester, the mean is always 72 to 74, somewhere in there. And the standard deviation is always 11 to 13, somewhere in there. Right? It's just, that's what it always is. Median, we haven't talked about median yet, but what is median? The middle number after you put them all in order, right? So it's also the 50th percentile. So 50% of the subjects had a heart rate less than 72. 50% had a heart rate greater than 72. Right? Here you see the max and the min and some various percentiles. We'll talk about those more when we get to those sections. So now I talked about bar widths or class widths. So let's explore what's it look like if you change that. So we did 10 already. Let's look at 4, and then 2, and then 1. When you have lots of data, you can have more bars, less width. So here it is, width 4. How does this compare to the one that you looked at before? Tells pretty much the same story, but it, more detail. You can see instead of there just being 120 to 130, now you're breaking at 124, and you see, well, there's one of those, and then it looks like there's actually, or the 124 would be in this one. There is a 120 in this, right? So this one's a 120, and then there's a 124 and a 126. So there's 2 people in this bar. So we had 3 really high pulses. The rest of it looks pretty bell-shaped and symmetric. This tail, that's called the tail of the distribution, this tail is longer than this tail. We'll learn to refer to that as skewness. Okay, and I forget your first name? Haley. Haley said something about a normal curve a minute ago, and a normal curve is the perfect bell-shaped symmetric distribution. It got named normal curve because you see it normally in a lot of measurements that you take, right? I mean, if you measure body temperature, you'll see a normal curve. When you measure lots of things, so that it got that name. So this one has a normal curve superimposed over the top of it, and it's a way of assessing, is this data normally distributed? And I would say, yeah, pretty close, but a little bit too much out here in this upper tail. Right? So there's some slight skewness. There's an oddity here with a bar that just got really shorter than you would expect, and that falls at 74, 76. So that would have been 74 to 76, 74 and 75, right? Less than 76. So 74 and 75, for some reason, there weren't very many of those. Just kind of an oddity in the data. But oh, one other thing that's kind of interesting to see on this is the ones that are multiples of 10 often spike a little higher. So 90, you get a spike. At 80, let's see, 78, there you get a spike, right? Because when people take it, if they are being lazy, they'll just round off to the nearest 10. Right. There's bars of width 1. Now, I told you we were going to make fun of you when you left her. Good luck. What do you see here that's a little bit strange? When you go bars of width 1, all of a sudden it looks a whole lot different. What do you notice? Yeah, you get a tall bar, then a short bar. then a tall bar, then a short bar. What's going on? Oh, no. What do you think? How are you supposed to collect the data? What did the instructions say to do for resting pulse?
Have them sit down for 5 minutes.
Have them sit down for 5 minutes, count for 30 seconds, multiply by 2. If you multiply a number by 2, what do you get back?
The double.
Even or odd? Even. There shouldn't be any odd numbers in this data. Guess what? There's odd numbers in this data. So where did you get odd numbers? I could pull up the spreadsheet and find several of you that turned in odd numbers. I won't do that, but it's fun. But so you have some odd numbers, but not near as many as you have even numbers. So that's something that all of the other histograms you couldn't see because the bar width was wide enough that it had both evens and odds in the same bar. When you go width 1, now it separates them out, and you can see that, oh, looky there, something weird. But other than that, you still see a nice bell shape with a long tail out this side. Now you can see exactly what these values are. This one's 120, this one's 124, this one's 126. Height. Here is summary statistics for height. Here is a histogram for height. Smallest person was about 56 inches. Tallest person was just under 80 inches. I think 79 was the tallest in the data set. Does this histogram look a little strange? It's not real bell-shaped. It's like sort of flat on the top. Or it goes up real steep and then down real slow kind of thing. What do you think's going on there? Okay, it could be that it's not representative of the population. But it actually is representative of the population. It's just I haven't summarized the data correctly.
Is it because it's both males and females?
It's both males and females. Very good. When you put two populations together that really aren't the same, you can get weird looking stuff. And that's a mistake that's made all the time when people analyze data. They don't realize, oh, I shouldn't be combining these two. That's apples and oranges. What do you know about males and females? Males are taller than females. So let's separate them out. There's females. Right? Look at where the center of the distribution is. Center of the distribution is what we would say is the typical or the average person. And since I have the normal curve, it's where the software would put the peak of the normal curve. So female average height is about 65 inches. 5'5". Right? It's interesting, there's a notch there. I'll come back to that in a second. If you look at males, look what happens. And this is like poor man's animation. Right? What do you notice? It shifts, right? The whole distribution shifts. It looks very similar, but it shifts. And how much does it shift? Well, the height for males is a little more than 71, maybe 71 and a half, right? So females are 65, males are 71. That difference is 6, right? So males are about a half a foot taller on average than females. It does not mean there's not overlap. There's definitely females that are taller than males, right? But on average. So here's a side by side, and you can see the two shifted, right? Now it is kind of interesting. Let's see, I'm not sure. Yeah, this one is all semesters since I've been collecting height, all put together, right? So that's a total of 2,300 males in there, and you still get this gap right there. What do you suppose is going on there? It was in females and males that right at the peak there was a gap. What would explain that?
You round the number.
Well, people do round the number, but look at where this gap is. It's hard to see these numbers, but this gap is at 71. The next one is 72. How tall is 72 inches? 6 foot. So if somebody is 5'11", what are they going to tell me their height is? 6 foot. Right? This is self-reported height. Right? So guys want to be 6 foot tall. Right? They just want to be 6 foot. So if they're not, they'll fudge it just a little bit. Right? So guys who are 5'11" rarely say they're 5'11". They say, oh, about 6 feet. The same thing happened with females, though, and that one I don't understand quite as well, but there's a gap right at 65, but it may be our minds tend to like even numbers better than odd numbers, so rather than be 5'5", I get more 5'4" and 5'6" than I get 5'5". But it's interesting that both of them are right at the average. Nobody wants to be average. They want to, I don't know, but okay. So this is all females put together, and the gap goes away then. In fact, the spike right before the peak, or right before the blue curve peak, is taller. That's 5'4". But we'll talk about this kind of a graph called a box plot in another section. But so here is the average. So for females, we had 226 females. And average height was just a little over 65 inches, 5'5", with a standard deviation of 3. So 65 plus or minus 3 is really common. Men, 71.45, also about 3 for standard deviation. So 71 plus or minus 3 is where the bulk of your population is going to lie. Okay. Now, what do you think about the age distribution? What is that histogram going to look like? Think about it. I will have questions on the test and say, here's a scenario. What do you think the shape of that distribution would be like? So height was very bell-shaped and symmetric, right? You have an average, and you have just as many people that are below average as you have are above average. What do you think about this age variable?
All over the place.
What did you say?
It would be
All over the place? True, but constant, so all ages are equally likely? That's called a uniform distribution. Okay, we'll see. Laura? Okay, so you think that all ages 18 to 90 are going to be pretty even? You got?
I would think that from like 18 to 20 should be higher because you have to do certain, pretty much certain age to start.
Okay. Think each of you think about, okay, who were my 5 people, right? Who did you mostly get? People around your age. And you're 18, 19, 20, 22, right? So what we're going to get is a skewed distribution. Symmetric and bell-shaped is one shape of a distribution. If it's not symmetric, it's said to be skewed. You get a really tall hump here at 18, 19, 20, 21, and then it tails off real slowly because there is no upper limit. There's a natural wall that I imposed at 18. But also, most people clumped up close to that natural wall. That imposes skewness in the data. What do you suppose this little secondary hump is here at, between 42 and 52? Parents. People who ask. How many people ask their parents? Yeah, about half of you, so good. Okay, I'm out of time, so we will pick up from there. Next time, the homework, like I said, is divided into two pieces, but on Monday I'll give you a better idea of which graphs you're going to expect in the first set and which you're going to expect in the second set.
I'm going to be gone.